In this video, I'm going to give you a basic introduction to capacitors. Okay, so a capacitor is an energy storage device. This is its circuit schematic. The circuit schematic is chosen to reflect this very basic physical structure to a capacitor. So this capacitor is constructed of two parallel conducting plates, and in between is an insulator, also known as a dielectric. Of course, there can be more complex and more efficient capacitor designs, but this is a basic one, and it helps us understand what's going on. Now let's consider the operation of a capacitor. Here we have a voltage V applied from a voltage source. We know that this is the positive side, so what that does is it attracts electrons from this parallel plate capacitor. So an electron can flow here and continue this way. When that electron is taken from the plate, it leaves a positive charge. At the same time, this positive charge attracts electrons on the opposite plate, and those come from the negative terminal of the battery or voltage source. And this keeps going, and we have a buildup of positive charge on one plate and a buildup of negative charge on the other plate. So on the positive plate, we get this buildup of positive charge, and that wants to hold tightly to the electrons that we're pulling off. So eventually it'll become harder to remove electrons from the positive plate, and the buildup of extra electrons on the negative plate repels additional electrons, so I can't just put more and more electrons onto that negative plate if I only have a certain driving voltage V. At some point, when we have some VC across here, we can't add any more charge. And from this picture, in this case, the VC is going to be equal to V, and we'll have some total charge of plus Q on the plus plate and minus Q on the negative plate. It turns out that VC is proportional to Q. So we'll write here that the charge stored on the capacitor is proportional to the voltage across the capacitor times some constant of proportionality C. That C is the capacitance, and maybe you can remember it if you arrange it like this. So looking at the Q over V, it kind of looks like an ice cream cone. The other thing I want to point out is that a current actually can flow in this circuit before we get to the point that there's no more charge that we can add to the capacitor on the bottom plate or remove from the top plate. Before we get to that point, I have an electron flowing to the negative plate and another one coming off the positive plate. So if you're the voltage source, you have no idea that electrons aren't moving in the circuit across the capacitor. You just see the flow of electrons coming into your positive terminal, leaving your negative terminal. So we actually do have a current, and the current, as you might recall, I equals the time rate of change in charge, and from above, it's the derivative of this. Now typically, C is constant, therefore we can bring it out of the derivative. And so we have this relationship that the current through the capacitor, yes, it's actually a current through the capacitor, is the time rate of change of the voltage across the capacitor. So in the circuit as we've drawn it here, the flow of electrons is counterclockwise, so the flow of current, I, is clockwise. So that's the I that we've got here, and then this Q is the Q in our derivative. One other thing I'll state about this is steady state operation. In steady state operation, the voltage across the capacitor is constant. So that derivative is 0, and that means then that the current flowing through the capacitor is 0. And that is very much like a open circuit. So the circuit looks like this, but in the steady state, it looks like this. And we'll just go ahead and mark this voltage VC and this current I. You can see from the circuit that we should expect VC to be VS. I'll make that a VS. And then I is 0 in steady state. This relationship may not always be true, especially if the circuit has different components in it, but current can't flow through the capacitor in steady state, and its voltage is constant. In this case, the capacitor voltage is the source voltage. You can imagine something different in there, like the capacitor voltage could be based on a voltage division or something like that. Okay, so that's some basics about the operation of a capacitor. We showed you what a capacitor is, and we showed you how it can behave in a very simple circuit, and how it will build up charge until the voltage you apply can't add or remove any more negative or positive charge. Because of this equation, if you turned up the source voltage, well, you could add more charge, you could store more charge, but that's not part of the discussion here. And then we talked about how the current and the voltage across the capacitor are related. And finally, steady state operation. In steady state, a capacitor behaves like an open circuit. One other thing I'll mention is that we can calculate the instantaneous power delivered to the capacitor. So of course we have to use the passive reference convention. So this VC should be defined with a plus and a minus sign. I was not careful when I wrote that in earlier. For a capacitor like this and some current flowing through it, well, it's simple. P is equal to voltage across the capacitor and current through the capacitor. Okay, so there you have it, basic introduction to the operation of a capacitor.